Calculus BC, we're looking at lesson 4.3, the first of 3 videos on this section. You can look at our learning targets at the top. I can find local extrema using the first and second derivative tests. For this video, we're actually going to be using the first derivative test, but there's a lot more material coming down. We can also find concavity. First things first, a very important definition. If f is continuous on a closed interval, if you can take derivatives on the open interval, then when your first derivative is positive, greater than 0, for every x value in that region, in that interval, open interval, then f is increasing on the closed interval. By the way, when we're talking about intervals of increasing and decreasing for f, we're always going to be using closed intervals. Now, why that is true, I hope is going to be pretty obvious. If you have, for every x value on an interval, that the tangent line slope will be positive, that f prime is positive, that naturally will mean that as you move left to right, you would expect your curve to go upwards. That's another way of saying that f is increasing. Likewise, if the first derivative is less than 0, if it's negative for every x value in that open interval, then we can say f is decreasing. Again, if that's the case, we'd always have a negative tangent line slope. We would expect as we go left to right to see our curve go down. So this is a very useful tool to talk about where a function is increasing or decreasing. Again, we're going to use closed intervals to communicate that. Obviously, if you ever go towards infinity, we'd leave that open because you cannot really have x equal infinity. The first derivative test, though, my goodness, what an important test this is. Let c be a critical number for f. In other words, find your derivative, find where your derivative could be 0 or undefined at those c values. What you're going to really realize is as long as f is continuous at that c, at that critical number, and differentiable, then you can get one of 3 scenarios here. If the derivative at c changes from positive to negative, then f of c is going to be a local maximum. You'll have a maximum value. If the derivative, f prime, changes from negative to positive at x equals c, then f would be a local minimum. Finally, if f prime does not change sign, if it's always positive or negative, except possibly at x equals c itself, then we do not have a local extremum. We don't have a local maximum or a local minimum. Let's see this in action and see what exactly is happening. We have example 1. I'm going to take a derivative, and we're going to do so using the product rule. So we'll have our first, here's our u, this is x. v prime, we have to bring down 2/5, and then have 1 minus x. Subtract a 1 from your exponent, you'll have negative 3/5, but don't forget the chain rule, the derivative of the inside, the derivative of 1 minus x is simply negative 1. So here's your u, and then here's your v prime. Then we'll have u prime, well, the derivative of x is simply a 1, and then we'll have v, which is 1 minus x to the 2/5. Well, our goal is to find where our derivative could be 0, where our derivative could be undefined. So, tell you what, let's take a look at negative 1 times 2 times x. We'll have negative 2x up on top. Down below we have a 5. But then this 1 minus x, I'm going to drop down to our denominator and just have that as 1 minus x to the 3/5. As we multiply through by our 1, of course, we'll just have a 1 minus x to this 2/5 here. And again, what you want to do, we talked about this in the earlier section, you'd really ideally like to get a common denominator. You'd like to get a unit fraction because you're interested not just where your derivative could be 0, but where your derivative is undefined. And because I'm looking here, I can see very clearly that my least common denominator in this problem is a 5 times 1 minus x to the 3/5. This second fraction is missing everything, so I'm going to multiply by 5, 1 minus x to the 3/5. And hopefully you're going to see some good things happen. You're going to notice now, of course, we do have one common denominator. That's nice. That was what we were hoping for. Here I've got my negative 2x. But look what's about to happen here. If you look at 1 minus x to the 3/5 times 1 minus x to the 2/5, I hope as I write up here 1 minus x to the 2/5 times 1 minus x to the 3/5, I hope you quickly look at that and say, adding the powers, that's just 1 minus x to the 5/5. But don't forget you also have a 5 here. So, if you had a 5 out in front, you'd have to distribute that 5. So we'll say plus a 5 and then minus a 5x. And what you're going to see very quickly is this becomes 5 minus 7x all over this 5 times 1 minus x to the 3/5. So that's your derivative right here. To find critical numbers, however, you're interested in where your numerator could equal 0 and where your denominator could equal 0. Where the denominator is going to equal 0, that derivative will be undefined. The numerator, if the top is equal to 0, well, it doesn't take you too long to see that x would be 5/7 for that one. And I hope right here, if you divide by 5 and if you raise both sides to the 3/5 power, you're really saying 1 minus x is equal to 0, which is saying that x would equal 1. And here are your two critical numbers. So that's what we're always going to start off with our first derivative test. Where we proceed is we're going to do a number line. And I'm going to very quickly just write that over here we have 5/7, and over here we have a 1. And it is the first derivative test, so we're going to plug in test values on these intervals into the first derivative. So to the left of 5/7, maybe the easiest number to check to plug in would be a 0. Between 5/7 and 1, maybe it would be easiest to plug in 6/7. And to the right of 1, maybe it's easiest to plug in a 2. And at this point, I do want to be super clear that we are testing the first derivative, so we're most concerned with what the derivative's value is when we plug in these test values. If you plug in a 0, your top here is just going to be a 5. Down below, I just have a 1 minus 0 is a 1, 1 to the 3/5. Suffice it to say, this whole region here will be positive. Notice what I'm going to do up above. We just said that when your first derivative is positive, that means f is increasing. So that is hopefully going to help you out. Now, as we plug in a 6/7, think about this. I'm going to maybe work way up here. We'd have 5 minus 7 times 6/7, and down below we have 5 times 1 minus 6/7 to the 3/5. 5 minus 6, well, that's a negative 1. And down below, 1 minus 6/7 is something positive. I don't even need to work this out in an exact form. I know that this plain and simply is negative. And what do we know then? We know that if my first derivative is negative on this region, that means f is decreasing. My curve is going down. Finally, let me do a little erasing. If we plug in a 2, now be careful. This is where kids can get into some trouble. The trouble that kids get into is that they only look at the top. You plug in a 2, and of course 7 times 2 is 14, and 5 minus 14, you get something negative, right? 5 minus 14, you'd get negative 9. But down below, 1 minus 2 is negative 1, and negative 1 to the 3/5 power. It's like the 5th root of negative 1, which is negative 1. Raise it up to an odd power. Negative 1 to the 3rd power is still negative 1. The bottom line is this denominator is negative also, and a negative divided by a negative is a positive. Please realize that is necessary. When you're plugging in a value, you have to check the numerator and you have to check the denominator. But more to the point, this is what the first derivative test is all about. You now know your function's going up and then it's going down. Look at that. This is a top of the mountain. Look, the arrows show you that. Likewise, your curve was going down, but then it's coming up. What do you know? That's the bottom of the valley. That's your minimum. So here's what we can do real quickly. Remember, we had f of x was equal to x times 1 minus x to the 2/5 power. What I'd like to do is plug in 5/7 to find out what my y value is. So I'd have 5/7, 1 minus 5/7. Well, 7/7 minus 5/7 is 2/7. Look at that. Maybe not the prettiest looking y value. We've got that. 5/7 times 2/7 to the 2/5. Hey, when you plug in a 1, you get something much nicer here. 1 minus 1 inside the parentheses is 0. 0 to the 2/5 is 0. You just get a 0. So what did I do? I found the exact y values that we get by plugging in those x values. And the first derivative test says, look at the number line, look at the arrows that you just had. You just have to write this out in a very particular way. And the College Board requires us to write a sentence. We have to be super careful. Look at 5/7. We said, hey, the arrow went up and it went down. I've got a max. I'm going to write this. There is a local max of, now at 5/7, you had this real ugly y value. Of course, we could get a decimal approximation if we needed, but this is good enough. There's a local max of, always name the y value. The max value or the min value is a y value. And then tell where it occurs. You can say at x equals 5/7, and then we give the justification why. Because f prime changes from positive to negative. So that's your local maximum. We'd say there's a local max, name the y value, state where it occurs, give a reason. That's so important. One last thing we're going to do to wrap up the problem, look at what was happening right here at 1. You could see the picture shows you've got a local minimum. So I'm going to say there is a local min. What was the y value? Well, the local min of, when you plugged 0 into f, you got, and when you plugged 1 into f, you got 0. So sorry, a local min of 0 at x equals 1. Always name the y value and then say at that particular x value and then give a reason. We could say because f prime changes from negative to positive, I'm going to write it in a different way. I'm going to say because f changes from decreasing to increasing. So you can justify in either one of those ways. You can talk about the first derivative changing sign, or you can talk about f changing from increasing to decreasing or decreasing to increasing. Example 2 is actually the extreme value theorem. We're skipping that. It's from section 4.1. Find your critical numbers, plug in your endpoints, plug your critical numbers into f, and that would be your absolute max or min.